my colleague and working on the Professor Martin Zhao. And he received his bachelor degree from Tsinghua University in 2015. The topic of his PhD research is data-driven modeling of lithium intercalation materials. His research combines theory, numerical simulations, and data-driven methods to understand a variety of experimental characterizations and elucidate the fundamentals of electrochemical systems. He is also broadly interested in applied mathematics, modeling, and the computation of complex systems and their engineering applications. So Hongbo, the floor is yours. Thank you.
Okay, thank you, Gerard, for the introduction and invitation. You can see this right screen, right?
Yes, I can.
Okay, great. Yeah, so I'd also like to thank the organizers for creating such a platform and to provide opportunities for the young researchers to present their work. So today it's a great privilege and pleasure to be here, and also thank you to the audience wherever you are in the world. And I'm very delighted to present some of the work with regards to today's topic on data-driven methods to study batteries. So in my research, I interacted a lot with experimentalists who perform battery experiments at X-ray beam lines. So in the background on the left is actually a picture of the beam taken at the synchrotron. So as a data and modeling person, the question I'd like to ask broadly is, how can we fully utilize the data generated at the synchrotron facilities quantitatively and extract useful physical information and knowledge? Also like to stress the importance of physics here, also echoing Wei's talk, because I believe that a fundamental understanding of how batteries work is really going to be the key to the discovery of next generation materials. And the major challenge with batteries is that we all know that it's an inherently multi-scale system that spans many orders of magnitude in length scales. So starting from battery packs that serves to store the energy for applications in electric vehicles, and also individual cells within the battery pack. And within the battery, the electrode consists of microstructures, which I think we're going to hear more about today. And its length scale is in the order of millimeters or less. And the microstructure is composed of active materials where the chemical energy is stored in these nanoparticles. And of course, if you go further down, that they consist of crystal lattices that X-ray diffraction can study, which is also going to be discussed in this part of the talk today. So while we do have these very powerful batteries nowadays, there's still lots of challenges and opportunities. For example, you can see that the energy density has increased by about 2 to 3-fold over the past 20 years, and the cost has been decreasing at a pace of 20% per year. And so this has made the use of lithium-ion batteries a feasible method for energy storage. There's still a lot of work to achieve a wider adoption of sustainable energy and also e-mobility. So we need to overcome these challenges by gaining a quantitative knowledge at different length scales. We really need to gain a full picture of all of these length scales that I mentioned here. And I argued that this kind of knowledge will be largely driven by the enormous amount of data that we have that are generated at these different length scales. And so there are mainly two sources of data. One comes from experiments at the macroscopic scale. So for example, the current and voltage and how, for example, the capacity changes over the number of cycles. And we can learn, for example, physical parameters like diffusivity and exchange current, or to the more recent machine learning approach where we can predict the lifetime of batteries using only the voltage data. Another source comes from, which is going to be focused of the talk today, is it comes from a microscopic scale, such as these images taken at synchrotrons. And my talk will address what quantitative information can we learn from the data generated at the synchrotron facilities, and what computational approach should we take. So the first example involves in situ scanning and transmission, X-ray microscopy of nanomaterials as the battery undergoes charge and discharge. And this work is led by Professor William Chu at Stanford and his postdocs and students. So as the battery gets charged and discharged, lithium goes in and out of the lithium iron phosphate particle, which is a cathode material. And in the meantime, the X-ray shines on these nanoparticles in the cell. The X-ray absorption allows us to see the spatial distribution of lithium within these particles. And here is a movie of this process. And so these particles, they came from the same cell and same batch of experiment. And so they are actually played in simultaneously and it's interpolated in time based on 6 to 7 snapshots for each of these particles. And in total, it takes about a couple of hours to charge or discharge. So when we disconnect the battery and in the middle of a charge or discharge and allow the particles to relax and do the microscopy again, and you see that it phase separates into, it is a phase separated material and it phase separates into a lithium rich phase and a lithium poor phase within the particle. And this is driven by a tendency to minimize the chemical free energy. And from the microscopy imaging experiments and also other experiments, we know the two phases, the composition of the two phases in equilibrium very well. But the detailed functional form of the free energy is unknown, especially if you want to model this phenomenon. It's largely phenomenological at this point, and it cannot be directly measured because it's thermodynamically unstable. So therefore, our thought is, can we use these images which are taken when the system is out of equilibrium, when it's actively undergoing reactions? Can we learn the free energy from that? So let me illustrate it with a simpler example of phase separation. And the phase separation is driven by this double well free energy. And so if we start from a mixture with a 1-to-1 molar ratio, the free energy is concave and hence unstable and undergoes the so-called spindle decomposition. So I illustrated with two kinds of slightly different free energy landscapes. So one is symmetric, the blue curve, and the other one is the purple curve, which is asymmetric. And on the right are the simulations if you let it relax over time. And also the histogram of the concentration values. So notice that these two patterns are completely different at the beginning. And the evolution of the histogram for the asymmetric free energy on the right is also asymmetric. And so this shows that the early stage pattern actually is largely driven by this free energy landscape. And so we know that the pattern really can tell us a lot about the hidden information, such as the free energy, or the chemical potential, which is the first order derivative in this equation, and also the importance of diffusivity. So these two quantities, the d of c and g sub h of c, they determine this dynamics, and it's driven by diffusion. Since there's no other way of directly measuring the two, so I'd like to ask whether we can learn it from the image of these two from the images. And so we achieve this by taking a discrete number of images and try to minimize the error between the data and the model, while being constrained by this partial differential equation. So these two functions are the two unknowns that we're trying to learn. And on the left is the landscape of the loss function L in a randomly chosen 2D plane. Of course, the actual dimensionality of parameter space is much larger in order to represent these two functions. So the optimizer uses the gradient enhancing information to find the minimum. This movie shows the training process. The top row is the training data, and the bottom row is the model prediction at the current training step. So on the left are the two functions at that step, which is the solid lines, and the truth, which are the dash lines. And you can see that the optimizer is able to converge from a non-pattern forming guess to the solution to the truth in about 10 to 20 iterations. In fact, something that we're currently working on, it's unpublished, so I cannot present it, but something we're currently working on is to apply this method to the experimental images I showed at the beginning. And we have been able to actually obtain a good agreement between the theory and those images of nanoparticles I showed. And so the second part of my talk, the next example involves the use of X-ray diffraction and scanning transmission X-ray microscopy, although done in an ex situ way. And again, this is also done in collaboration with Professor William Chu's group at Stanford. So the material that we study is called lithium layered oxides, which the M here can be transition metals, a mixture of them, such as nickel, manganese, cobalt, which is a very common cathode material. And as the battery gets charged and discharged, the X-ray shines on this electrode, and it produces a diffraction pattern. For every 1 milligram of active material put in the sample, there are about hundreds and thousands of these agglomerate particles, and these micron-sized agglomerate particles. And each agglomerate particle consists of many single particles. So on average, you'll get like millions of these single particles. So very good statistics by shining the X-ray on the entire sample, the entire electrode. So the diffraction pattern that you see here, if we take one of the rings from this so-called Sprague's peak due to diffraction and see how it evolves in time. So this Bragg's peak location changes, it shifts because the lattice spacing of this crystal, of the crystal lattice of this material changes as a function of lithium concentration. So it shifts as with the addition and removal of lithium. As the battery charges and discharges. So what we find is that during slow reaction, this peak just shifts continuously and reversibly. So and this is what happens when it's close to equilibrium. And it does not phase separate, as you can see. It's just continuous change. But if we use a larger current, during lithium removal, the upper panel, the peak splits into two coexistent peaks. Whereas during lithium insertion, the bottom panel, the peak remains a single peak throughout. So we call this phenomenon fictitious phase separation because it is not a fictitious phase separation because it is not a thermodynamic phase separation, as you can see on the left. But we're not the first one to observe this. There have been already a number of papers have reported this, and some have attributed this phenomenon to diffusion-induced heterogeneity. Some have attributed to a mechanical effect. So to address these hypotheses, we looked at another sample. So we also have the data on these platelet single particles that are well dispersed, they're very dilute, and so they do not touch each other. And we also see the same trend here from X-ray diffraction. And so it's not really due to mechanical interaction among the particles. And another experiment our collaborators did was to use these platelet particles. And so when we charge them, when we stop the current and immediately take them out of the battery and out of the out of the electrolyte and let it relax, and then do microscopy on them, which shows basically the lithium distribution in the particle as similar to what I presented earlier. And what we see is that at the beginning, the particles are full of lithium. And then in the middle of the lithium removal, you see that on the left panel, when it's slow, when the reaction is slow, the lithium concentration shows a unimodal distribution. Whereas on the right, you see a bimodal distribution, which is consistent with what we see from the diffraction also. And also remember that the particles, they are internally equilibrated because they are taken out of the electrolyte. And so they cannot, so internally it's uniform, as you can see, but the different particles, they cannot talk to each other, they cannot exchange lithium once they're out of the electrolyte, right? And so this freezes the status of any heterogeneity between the particles. And this indeed shows that this kind of phase separation happens at among the particles. So it's interparticle phase separation and not intraparticle phase separation. And so when you remove more lithium, they both become unimodal again. And by reversing the direction, both slow and fast reaction shows a unimodal distribution consistent with the X-ray diffraction and all the way back to being full of lithium again. So what is the kinetic origin of the fictitious phase separation? So in the literature, people tend to favor a diffusion as the dominant factor. And indeed, what's also done in literature is that the diffusivity of lithium in these particles increases rapidly with decreasing lithium. And that leads to a shrinking core pattern where the outer ring, which has less lithium, because it has higher diffusivity, it has a very very little concentration gradient at the outer ring. Okay, let me illustrate what I mean by simulation, which I think will be clear. So during lithium removal, this shrinking core pattern does result in a bimodal distribution, which I plot on the right. Hence this bimodal X-ray diffraction pattern. And in the reverse direction, when the lithium is reinserted, the distribution is indeed unimodal. So it is consistent with experiment, with the X-ray diffraction experiment. However, we proposed this other mechanism, which is controlled by reaction. So say this reaction is increases rapidly with decreasing lithium concentration. So this reaction is autocatalytic. And in this case, when one particle is slightly ahead of others, they will react faster and faster because of this autocatalysis and leaving others behind. And it's also possible to form this kind of bimodal distribution. And and as you can see in this simulation, during lithium removal, there's this bimodal distribution. And in the opposite direction, the particles, if they're ahead, they will slow down, and the particles behind they will catch up, and so it's autoinhibitory, and that leads to this unimodal distribution. And this model, it can also explain the X-ray diffraction qualitatively, at least. And so, what is the difference? The difference between these two models is in where the phase separation or segregation occurs. So for the diffusion controlled model, the phase separation occurs within the particle. And so if you allow intraparticle relaxation, then it'll go back to a unimodal distribution. But for the reaction limited case, it's going to stay bimodal if you allow intraparticle relaxation, but don't allow interparticle exchange. And you can see this more clearly if you look at the histogram of the diffusion limited model. So it's bimodal overall, but if you allow intraparticle relaxation, if you look at the red box, it remains a unimodal distribution. And so this is the key qualitative difference between these two models. And so fortunately, we have this data set from the X-ray diffraction, from the STIXM microscopy images. And so we take these images and we take basically the lithium fraction histogram from these X-ray images and to perform a Bayesian model selection. So in this Bayesian model selection, all the parameters in this model, they are fitted. That includes the reaction, diffusivity, kinetics, and all the other parameters. They're all free to vary. And on the right, I show that the best fit result from these two separate models. Okay, and so you can see that the reaction controlled model can produce a bimodal distribution, but the best fit diffusion controlled model on the right is very poor. It cannot give you bimodal distribution basically. And by sampling the parameter space, but essentially calculating the Bayes factor, we find that the reaction controlled model should be accepted. And so once we determine the model, we can further simplify it with this reaction limit model. Essentially the concentration within the model, within the particles can be essentially modeled as a scalar because it's uniform within the particle. And it's controlled by the reaction rate R and also add some noise. And this can be converted to a Fokker-Planck equation, which is the evolution of the probability distribution, F as a function of a lithium fraction, C. So when this reaction rate is autocatalytic, so the R increases with concentration C, the distribution actually will expand. The F of C, it expands in time because essentially the characteristics of this advection equation, which are the gray curves, the trajectories, essentially the trajectories of lithium concentration in time for individual particles, you see that because of this autocatalysis, the gray curves, they diverge, and correspondingly the probability distribution will follow that trajectory, and it also broadens and form this bimodal peaks. So we can use actually this Fokker-Planck equation to interpret the X-ray diffraction, because the X-ray diffraction essentially tells us the lattice parameters, and lattice parameters, as I mentioned, is really indication of lithium concentration. Okay, and so we can actually use this kind of data set to inversely learn the reaction kinetics, because the reaction rate R is actually the unknown here. And so by doing that, by doing this, the same kind of partial differential equation PD constraint optimization, here is a result, a comparison between the model predicted X-ray diffraction and the data. And you see a good agreement. So conventionally, you can't really, if you charge the battery at a fast rate, especially conventionally, if you can't really use the electrochemical methods, because typically we assume whenever do this kind of typical learning, we assume that it's a unimodal distribution or even a delta distribution, but here it's not the case. So we have to sort of constrain this process by subjecting it to this partial differential equation, which we know will work for this system. And so here's the result of the exchange current, which is a part of that reaction kinetics R in the equation. So the results for these two kinds of particle morphologies I showed at the beginning. So one is the platelet particle, the other is a conglomerate particle. They're consistent and they both increase rapidly with decreasing lithium fraction. In fact, this is also validated by another set of measurements done in the linear regime. So very small perturbation electrochemical methods, EIS, which is the impedance, and the PITT step change, very, very small perturbation around equilibrium, and they're both consistent. And so with this knowledge of autocatalytic reaction kinetics, we can further make predictions beyond the training data and predict essentially where the fictitious phase separation occurs. So which is the red region here. So when the rate of deinsertion is fast enough, the distribution is bimodal, and during lithium insertion, the distribution is always unimodal. So in summary, I showed that we can combine this data analytic method here. In this case, I talked about PD constraint optimization and combine it with theoretical models, although with some constitutive relations in the model that are unknown, which is what we try to extract, things like free energy, reaction kinetics, and diffusivity. And we try to learn that from images or X-ray diffraction. And we're also looking for other applications of this general method. So if you're interested, and if you have images or other data sets that you think can yield more quantitative information through this method, so please let us know, right? Because we're constantly looking for other applications. And I like to acknowledge that my work is funded by Toyota Research Institute, and these are the people that I also introduced earlier that I work closely with on these projects. And so with that, I'll end here. And be happy to answer any questions.
Thank you, Hongbo. This is very informative, and I think it's exactly 30 minutes. So I'm afraid there will be probably no Q&A after this. And after all the talks we can have a more general discussion, and also there will be opportunities for the audience to ask you questions. Is that okay?
Yeah, sure.
Okay, yeah. So then we will go to our third presentation, which will be